The world around us moves with an almost invisible precision. Cargo ships the length of 4 football fields glide silently into port, loaded with 24,000 containers. Trains, stretching for miles, pull 60,000 tons of ore across vast continents. Aircraft, each weighing hundreds of tons, lift into the sky at 600 miles per hour. These movements, so commonplace, are in fact miracles of engineering, born from radical innovation. They defy the immense forces of friction, gravity, and inertia, pushing the boundaries of what is possible. For centuries, humanity sought more efficient ways to bridge distances, to carry more, faster, and further. We built bigger engines, stronger materials, and grander schemes. But it wasn't raw power alone that unlocked this scale. It was a series of ingenious solutions that redefined how we harness the fundamental laws of physics. These are the 6 engineering innovations that changed how we move everything. Number 6, the tunnel boring machine. Imagine a colossal steel cylinder, over 50 feet in diameter, slowly grinding its way through solid rock beneath a city. Before the advent of specialized tunnel boring machines, or TBMs, constructing tunnels was a dangerous, slow, and labor-intensive process, reliant on drill and blast methods that could barely advance a few feet a day. The ground was unstable, the work deafening, and the risks immense. Engineers faced a fundamental problem: how to excavate massive volumes of earth and rock while simultaneously supporting the newly exposed tunnel face against immediate collapse. The answer was not simply a bigger drill, but a moving underground factory designed to cut, clear, and reinforce all at once. The trick lies in the TBM's shielded design and continuous operation. At its front is a rotating cutter head, studded with hardened steel discs and carbide tips, which grinds against the rock face. Behind this, hydraulic rams push the entire machine forward, bracing against the completed sections of the tunnel. As the cutter head turns, excavated material is fed onto a conveyor belt that runs through the body of the machine, depositing the spoil into wagons or pipelines for removal. Crucially, immediately behind the cutter head, the TBM erects precast concrete segments, forming the permanent lining of the tunnel. This means the tunnel is excavated and supported almost simultaneously, leaving minimal exposed ground. The world's largest TBMs, like those used for projects such as the Gotthard-based tunnel in Switzerland, are over 1,600 feet long and can bore through various geological formations, advancing at rates exceeding 100 feet per day. The Gotthard-based tunnel, for instance, is the longest and deepest railway tunnel in the world, stretching over 35 miles, and was only possible due to the continuous, integrated process of the TBMs. Without these subterranean giants, megaprojects like urban subway systems, underwater road tunnels, and transcontinental rail links would simply be economically and practically impossible. Number 5, the heavy lift crane. Picture a single machine lifting a fully assembled oil rig module, weighing over 20,000 tons, directly from a barge onto a waiting ship. For millennia, lifting heavy objects was a laborious affair, limited by sheer muscle and simple levers. Then came steam, then hydraulics, but the scale of the challenge grew with our ambition. Modern industrial modules, entire sections of power plants, and offshore platforms are too massive to be built on site. They must be constructed in specialized fabrication yards and then transported and lifted into place. The engineering challenge is immense: how to manage and distribute the colossal compressive and tensile forces involved in lifting objects that could crush smaller structures instantly. The core innovation is not just brute force, but precise load distribution and stability. Heavy lift cranes employ complex lattice booms and counterweight systems to balance enormous loads. Their secret lies in managing leverage and preventing buckling. A crane's lifting capacity isn't just about the strength of its cables, but the structural integrity of its boom and the stability of its base. The world's largest offshore heavy lift vessel, the Sleipnir, uses 2 massive revolving cranes, each capable of lifting 10,000 tons, totaling 20,000 tons in a tandem lift. These cranes operate on a ring-based slewing system, distributing the immense weight across a vast area of the vessel's deck, preventing localized stress that would buckle smaller structures. The booms themselves are intricate trusses of high-strength steel, designed to resist compression and tension across their entire length. This allows engineers to build components in controlled environments and then precisely position them, dramatically reducing construction time, cost, and risk, especially in challenging offshore or remote locations. Number 4. Advanced pipeline systems. Imagine a continuous, unseen river of crude oil, millions of barrels strong, flowing thousands of miles from remote extraction sites to refineries and ports, 24 hours a day, 7 days a week. For much of human history, transporting liquids like oil or water over long distances was an arduous task, requiring countless barrels, wagons, or even ships. The problem was not just volume, but friction and maintaining pressure across immense distances and varied terrain. How do you keep a fluid flowing efficiently without it losing all its momentum or requiring an impossibly large initial push? The genius of modern pipeline systems lies in a combination of high-strength materials, precise pump station placement, and sophisticated flow dynamics. Pipelines are not just simple tubes, they are meticulously engineered networks. The steel pipes themselves are often several feet in diameter, coated internally to reduce friction and externally for corrosion protection. Crucially, pump stations are strategically located along the pipeline's route, typically every 50 to 100 miles, to repressurize the fluid and overcome the frictional losses that occur as the fluid moves through the pipe. Each pump station contains powerful motors driving centrifugal pumps that boost the pressure, allowing the fluid to continue its journey. Advanced control systems monitor flow rates, pressure, and even the temperature of the fluid in real time, adjusting pump speeds to optimize efficiency and detect leaks. The Trans-Alaska Pipeline System, for example, is 800 miles long and moves up to 2.1 million barrels of crude oil per day through 3 to 4 feet diameter pipe, using 11 pump stations to push the viscous liquid over mountains and across permafrost. These invisible arteries are far more efficient than any other transport method for bulk liquids, operating with minimal human intervention and delivering continuous, reliable supply. Number 3. The modern freight train. Consider a single locomotive, no bigger than a large truck, pulling a train over 2 miles long, carrying enough cargo to fill 250 large semi-trucks. The earliest trains were limited by the power of their steam engines and the strength of their couplings. As industrialization boomed, the demand for bulk transport grew exponentially. The fundamental engineering challenge was friction, how to move immense weights over land with minimal energy expenditure. Road transport, even with modern trucks, faces significant rolling resistance. How do trains achieve such monumental efficiency? The answer lies in the exceptionally low friction between steel wheels and steel rails. This unique interface creates an efficiency advantage that is unmatched by any other land-based transport. A steel wheel rolling on a steel rail experiences only a fraction of the rolling resistance compared to a rubber tire on asphalt. This means a single horsepower of energy can move significantly more weight on rails than on roads. But it's not just the wheels, modern freight trains are also masterpieces of distributed power and braking. Contemporary diesel-electric locomotives, like the Evolution series from GE Transportation, generate thousands of horsepower. Often, multiple locomotives are placed throughout a long train, not just at the front, using a system called distributed power, DP. This allows the engineer to control all locomotives simultaneously, improving traction, reducing stress on couplers, and enabling longer, heavier trains. A single modern freight train can haul over 30,000 tons of cargo, a feat that would require hundreds of trucks. This incredible efficiency makes rail transport the backbone of heavy industry, moving everything from coal and grain to automobiles and intermodal containers across continents with unparalleled fuel economy. Which of these machines would you least want to be standing next to? Tell me below in the comments. Number 2, the jet engine. Witness a massive aircraft, fully loaded with fuel and cargo, accelerating down a runway, then climbing at hundreds of miles per hour to an altitude of 35,000 feet. For centuries, flight was a dream. Early aircraft relied on propellers, which are efficient at lower speeds and altitudes, but become incredibly inefficient as air density decreases and speeds increase. The core problem was thrust. How to generate enough forward propulsion to overcome drag at supersonic or near supersonic speeds, and how to do it efficiently enough to carry thousands of miles of fuel. The jet engine solved this by fundamentally changing how thrust is generated. Instead of pushing air with blades, it sucks in vast quantities of air, compresses it, mixes it with fuel, ignites it, and then expels the superheated exhaust gases at tremendous velocity. This process, known as the Brayton cycle, creates forward thrust according to Newton's third law of motion. For every action, there is an equal and opposite reaction. Modern turbofan engines, like the General Electric GE9X, the world's largest, boast fan diameters of over 11 feet and generate over 100,000 pounds of thrust. The critical innovation is the bypass ratio. A significant portion of the air drawn into the engine bypasses the combustion chamber entirely, passing around the core and mixing with the exhaust. This bypass air greatly increases propulsive efficiency, reducing fuel consumption and noise. These engines enable aircraft to cruise at altitudes where air resistance is lower, allowing planes to fly at speeds around 600 miles per hour, covering vast distances in a fraction of the time conventional transport would require. They revolutionized global travel and logistics, making intercontinental journeys commonplace. Number 1, the container ship. Imagine a floating city of steel boxes, 24,000 of them, stacked 10 high, sailing silently across an ocean. Before the container, global trade was a logistical nightmare. Every port was a chaotic scene of stevedores manually loading and unloading individual crates, sacks, and barrels, a process that was slow, expensive, and prone to damage and theft. The fundamental problem wasn't the ship itself, but the inefficiency of the interface between land and sea transport. How could cargo be transferred seamlessly and rapidly, allowing ships to spend less time in port and more time at sea? The answer was astonishingly simple, yet revolutionary: standardization. The invention of the intermodal shipping container, initially championed by Malcolm McLean in the 1950s, standardized the size and shape of cargo units. These containers, typically 20 or 40 feet long, can be loaded onto trucks, trains, and ships with equal ease, using specialized cranes. The engineering breakthrough wasn't in building a bigger ship, but in creating a system where the cargo itself became a modular, interchangeable unit. Modern container ships, like the Ever Ace class, can carry up to 24,000 TEUs, 20-foot equivalent units. The sheer scale is mind-boggling. If all the containers on a single megaship were laid end-to-end, they would stretch for over 90 miles. This standardization means that a single crane can unload and load a container in minutes, rather than the hours or days required for breakbulk cargo. This dramatic reduction in port turnaround time, combined with the ability to transport goods securely and efficiently across multiple modes, slashed shipping costs by 90%, creating the backbone of our globalized economy. Without the container ship, the vast majority of goods we consume daily would simply be too expensive, if not impossible, to transport. It is the invisible force that underpins nearly everything we buy, sell, and use. The machines that move the